Okay, now airborne gravimetry, or I would say it's better scalar airborne gravimetry. So in scalar airborne gravimetry, we measure gravity disturbance, and we can determine down the geoid or gravity anomaly. But how? First, we need to determine or find the mathematical relation between these quantities. Simply, if you remember, based on Brown's formula, divided by gamma, delta G and M was N plus R, T and M, and gravity anomaly will be N minus 1 R, the T and M. So if you want to solve the boundary value problem of gravimetry, or airborne gravimetry, the question is that we have gravity, we have the Laplace equation outside, and the solution of Laplace equation, or for the T, let me say T is a spherical harmonic solution, but what we have is the gravity disturbance at airborne. So how do we do that? Let us focus on determining geoid from airborne data. It means that we need this formula and this formula. First, we determine the relation between the harmonics of the geoid and gravity anomaly. But how? TNM is constant, is common in both. So simply, if my goal is to determine geoid height from airborne gravimetry, it's better to determine this one. So I solve TNM from this equation and put it inside this formula. So I will have 1 over gamma here, and R divided by N plus 1 times gravity disturbance. So this is the main equation that we need to use. Already know that we already know the spherical harmonic expansion of the geoid, and it is, and let me write it, N is equal to a double summation of n from 2 up to infinity, and double m minus n till to m, and n and m, y and m. So that's enough that to put this n and m inside this spherical harmonic expansion. Therefore, we come to a new formula, and which is n is equal to, let me write double summation over m. I have it in, no, not double summation. It will be confusing then. So an m1 over gamma r and 1 over n plus 1 delta G and M. However, there is something that we need to explain here for you, because this equation that I wrote here is valid for the case that the gravity disturbance is at the surface of the sphere. But we are talking about airborne level. This one, airborne. So this gravity anomaly, this formula that we write it here, is for the case that at, let me see, at sea level, or at the boundary. So let me explain how to derive the spherical harmonic coefficients of the airborne data. So to see how the height can affect this formula. So let me take away this one. Think that this is the Earth's sphere with the radius r, and we have an aircraft here flying at the geocentric distance r. The disturbing potential at this airborne level can be written like that. We already have that equation for the potential m minus n t and m y and m. So, and gravity disturbance is minus the derivative of. Then I take the derivative of this formula. It will be delta G minus, I take the derivative, it will be m plus 1 over r plus r, m plus 2. 1 minus is created here, I will go here, and t and m y theta and lambda and sigma. So, and you see, what you see here is this one. This one I wanted to emphasize on. When you take the second order, the first derivative, this downward continuation or upward continuation factor, damping factor appears, and it is m plus 2, not m1, m plus 1. That's the thing that we have to consider. So, if I want to write the mathematical model for or spherical harmonics relation in spherical harmonics at the potential at airborne level, let me write it, and T and M let me write it like that. It's a peel, not peel, it's an arrow, upward arrow. Let me clean it. Is n plus r over r n plus 2. That is the main equation. Oh, something is missing again. Place. And it is gravity. No, this one is gravity disturbance. Let me click it first. No, it is a correct one. So in the case that we are at the surface, not at airborne level or above this equation will be like that. Simple. But as you see, based on this derivation, the spherical harmonics spherical harmonic coefficients of the gravity disturbance at the airborne level has a term which this term, oh my god, has this term. This is called upward continuation factor, or damping factor. What does that mean? It means that when you are at higher level, this ratio will be smaller than 1, and it will, when n increases, it will kill frequencies of the TNM. And this means that when you are at outside the sea, outside the boundary, or far from the Earth, the gravity or the potential both are smoother than the case that you are at the surface of the Earth. So that was the main equation to drive. Now I will insert this back. I want the geoid at the surface, not at the airborne level. And the formula for the geoid was this. The geoid height, summation n summation over m minus n, and it was 1 over gamma here, and we have T and M here, y and m, theta and lambda. So I solve T and M from this equation and insert the result back to the formula for the. So if I solve T and M, the result will be R over n plus 1, R over R, n plus 2, delta G and M at airborne level. So if I insert it here inside this equation, inside n, then I get n is R over gamma sigma n from 2 up to infinity, 1 over m plus 1 r small r over r n plus 2, and here minus n to n delta g and m y and m theta and lambda. Note that delta g is at airborne level. So at airborne level, if we have a sphere at the airborne level, we can simply write this equation of harmonics again. Even at airborne level, it is correct. And it is delta G and M at airborne level will be 1 over 4 pi integral delta G at airborne, theta prime lambda prime, y and m, theta prime lambda prime delta. So if I insert this back here and apply the, after that I will apply the addition theorem of spherical harmonics, I will get this equation. N is 1 over 4 pi gamma integral n from 2 to infinity. So we have 2n plus 1, n plus 1, r over r, n plus 2, P and cosine theta, and gravity disturbance at the airborne level, d sigma. That's the integral formula for determining the gravity, determining the geoid from airborne gravimetry data.